configs on all devices. Following that, load the troubleshooting lab number. Welcome to CCNA Troubleshooting Lab number 6. If you haven't already done so, please load the OSPF working configs on all devices. Following that, load the Troubleshooting Lab number 6 configs on all devices. So in this particular lab, we have a problem of R3 not able to ping R2, with the loopback 0 of R3 being the source, loopback 0 of R2 being the destination. So just to show that to you graphically, what we're talking about is R3 sourcing its pings from here is not able to get those pings to here. So let's try that out and see if that is actually the case. So we'll go here onto R3 and we'll do a ping sourced from loopback 0, and we can see that that ping fails, just like the problem says. Now looking at our lab restrictions, we can't change the physical layer, can't bring any interfaces up or down. Existing access lists, we can modify individual entries, but we can't delete or add new ACLs. The finished working lab must adhere to the original lab specification, so this assumes that you've already gone through the monster lab where we built everything up from scratch. And loopback 0 on R3, which is sourcing these pings, is considered to be a private network, translated via NAT, and should not be known beyond R1. So this tells us a very critical point. If a customer's network was doing network address translation and translating some private networks before those packets were able to go into the public internet, clearly if you were to troubleshoot that, you would have to have that very relevant piece of information up front. If you don't know that NAT is going on somewhere in the topology and which networks are being translated by NAT, you might be led down a rat hole of trying to troubleshoot routing problems when in reality the problem might not have anything to do with routing whatsoever. So it's very important that we realize that this particular network is intentionally not supposed to be known beyond router 1. So if we go here, we are told that this particular network is private. Router 3 clearly knows about it because he's directly connected. Router 1 should know about it, but no other devices on this side of this circle should know about that network. So that tells us that router 1 is most likely the router that's doing the network address translation of this private network. So the first step in our troubleshooting is to make sure that router 3 actually has reachability to router 1. Let's see, when router 3 does his pings to network A, what does his routing table say? Where is he supposed to forward those packets? Hopefully he's supposed to forward them to router 1. So let's just check that out. So we go into router 3, show IP route, and we see that yes, router 3 has a default route. Anything he doesn't know about, which clearly subnet A falls into that category, he's supposed to forward them to router 1. .62 is the IP address on router 1. So if we take a look at our diagram, .62 is the address right here on this point-to-point subinterface. That is .62. So that's where router 3 will forward his traffic. So first step is, can router 3 even reach that next hop? Just because that next hop is in his routing table doesn't necessarily mean it's actually reachable. So let's try pinging it to see if we can get there. And it is. It's reachable. Okay, so let's go to router 1 now and see if router 1 can reach subnet A, which is our ultimate destination. Ping 190.190.8.1. And yes, router A does have reachability. So we know now at this point that when router 3 sends his packets sourced from this address, they will go to router 1 because router 3 only has a default route. Once they go to router 1, we know that router 1 does have full reachability to get to this subnet because we just pinged it from router 1 and we saw that ping was successful. Now we know that router 1 is supposed to be doing network address translation. And how do we know that? because it said subnet K was private, only supposed to be known by router 1. Anything else beyond router 1 should not know about subnet K. So that tells me that router 1 is most likely doing the NAT, the network address translation. So let's go ahead and go on router 1 and just do a quick peek at his configuration and see if we can spot some NAT config in there. Okay, and here I do see a NAT command right here. Now that doesn't tell us that NAT is correctly configured. All we know is that this router does have some NAT on it. So at this point, I would focus in my troubleshooting on network address translation, see if this guy is correctly configured for a translation. Well, clearly he's not, otherwise the pings from router 3 would make it to router 2 and back. So let's see. So we know that according to our topology diagram, that when router 3 sends pings sourced from here, they're going to come in on serial 1/0.132. So I would consider that to be the NAT inside interface. Let's make sure that it really is configured as NAT inside. So that was .132. Here it is, serial 1/0.132. And yes, we do have it configured as NAT inside. Now, if router 1 is going to translate these packets when they come in an inside interface, they have to be leaving on a NAT outside interface. So we already saw that router 1 was able to ping subnet A. The question is, what interface does he use to reach subnet A? Because that is what our outside interface should be. So it looks like he's using serial 1/3. So doing translation, that would be considered our outside interface. Let's see if it is defined that way, serial 1/3. It is IPNAT outside. So far, our inside and our outside categories are correctly defined by NAT. So in NAT, we've seen that this interface right here is configured as inside, and this interface right here is configured as outside, just like we would expect. Okay, but as far as NAT's concerned, that's just part of the puzzle, correctly defining the inside and outside interfaces. The next step is, does NAT know, has it been configured to know that when it sees packets from this source, that it should be translating them? Well, let's take a look. So let's go in router 1 and see if it knows that packets from the 8.128 network should actually be NATed. Okay, so that would be in our IPNAT inside command. And right here we have IPNAT inside. So this says any packets that match access list 101 should be translated. All right, let's take a look at access list 101. This says permit ICMP, that's good, they're pings, from a source of 190.190.9.128 with this subnet mask. Now if you look real closely, you'll realize that we have a problem right here. 9.128, but that's not where these packets are coming from. These packets are coming from 8.128, not 9.128. So the packets from subnet K will not match the access list, which means they will not be translated. They'll go out as normal. So as they go through router 1, they're not going to be filtered or dropped. They'll just go out as is. But we've been told that 8.128 is a private network, that other routers on this side of the line don't know how to reply back. Is that true? Well, let's see. Does router 2 have a route back to 8.128? It should not, because that's a private network, but let's see if it does. Show IP route. We're looking for a route to the 8.128 network. All right, looking through here, I don't see 8.128. Now he does have a default route going to 9.65. That is our HSRP active router, which is switch 2. So let's see if switch 2 has a route back to the 8.128 network. All right, so in switch 2, I do not see a route back to the 8.128, which is good because that's a private network. We should not be seeing that in any of these routing tables. Also, switch 2 does not have any default route. So, right now we've identified one of our problems. The problem is that packets being sourced from subnet K are using a default route to reach router 1. Router 1 is inspecting those packets to see if they should be NATed. It is not finding an access list that matches those packets, so it's just routing them out unchanged. And then the destination of subnet A is known by everyone, so eventually those packets do make it to subnet A. When router 2 tries to reply to those pings, he then sends those replies to switch 2, which is the HSRP active gateway, and it drops it because switch 2 doesn't have any route back to our private subnet of K. So we need to get router 1 to NAT these packets like he's supposed to. So our first step is let's change that access list to be correct. The access list is wrong in router 1. So let's change it to be right. Let's go back to router 1. Show run section access-lists. Okay, so that's the one that's wrong. So we'll say no, we'll just get rid of that. No access list 101. And now let's paste it back in, but this time changing that 9 to an 8. Okay, so let's review. We already know that NAT inside and NAT outside have been correctly identified on this router. And now if we scroll down to the bottom, there we go. Now IPNAT inside says match packets matching access list 101. And access list 101 now is correctly configured to match packets from loopback 0 of router 3. So let's see, is that enough? Will that work? And by the way, what's going to happen then? Once those packets are matched, their source address will be swapped out for the source address of loopback 0. We're actually doing port address translation here. So loopback 0 will be used. Okay, so let's see, do our pings work from router 3? No, they're still not working. Is our translation happening? Is NAT doing what it's supposed to do on router 1? Show IPNAT translation. Yes, there is a translation. Here was the original source, 8.129, and it was translated to 8.225. And if you look at the diagram, 8.225 is exactly what it's supposed to be translated to. Loopback 0 on router 1. So it is being translated. So why is this failing? Okay, well we know that router 1 has full connectivity over here to subnet A. So now when these packets get here to subnet A, we know they're going to have a source address of 8.225. Does router 2 know how to respond to packets that came from 8.225? Let's take a look at router 2. Show IP route 190.198.225. Subnet not in table. But remember, this guy did have a default route, which pointed him over to his HSRP active gateway, which was switch 2. So let's go over to switch 2 and do the same command and see if switch 2 knows how to get back to this route. Subnet, not in table. So here we're having the same problem as we had before, where if we take a look at our topology diagram, now at this point, when the router 3 sources these packets here and sends them to router 1, they're being translated to this address. And then as they leave here from this address, they're getting to our destination. And then when the destination goes to reply to those packets, he's sending them right here to switch 2, and switch 2 is dropping them. Now, there was nothing that said that subnet M should be private. As a matter of fact, it can't be private. If subnet M is what our private networks are being translated to, then that means that everybody on this side of the line needs to have reachability back to subnet M. So why does switch 2 not know about subnet M? Well, let's go back to router 1. It's router 1's job to advertise subnet M into OSPF to give everybody else reachability to it. So let's check and see if he's doing that. So we will go back to router 1 and issue the command show IP OSPF interface brief. Let's see if loopback 0 is included in our OSPF interfaces. And it is not. Loopback 2 and loopback 1, but loopback 0 is not here. So this is the problem. The second problem, I should say. The second problem is that router 1 is using NAT. He's translating packets to a new source address of his loopback, but nobody on this side of the line knows about that loopback because he's not advertising it into OSPF. So let's go ahead and advertise that into OSPF to give reachability on the return path of those packets. Router OSPF1, network 190.190.8.224, that's his loopback 0, 000.31, and that belongs in area 1. If you remember the original design, all links on router 1 and all links on router 3 were originally in area 1. Okay, now if that loopback has indeed been advertised throughout the entire topology, now when router 3 does his ping and is translated by router 1, he should get replies to those pings. Let's find out. And success. It is working. So we had several problems here. Traffic that was supposed to be natted by router 1 was not working because the access list was not matching the traffic. And then secondly, once we did get the access list working, we were translating the traffic. However, we were translating it to an address that nobody else knew about, so we couldn't get our reply traffic back. So that's how we fixed that troubleshooting ticket. Welcome to CCNA Troubleshooting Lab number 7. If you haven't already done so, please load the OSPF working configs on all devices and then load the Troubleshooting Lab number 7 configs on all devices. So the symptom of the problem here is that R2 cannot do an IPv4 ping to loopback 2 of R1, which is the 3311 address. So let's go ahead and try that out. R2 cannot ping R1. And we see that the ping does not work. So now looking at our restrictions before we start changing anything, can't change the physical layer, can modify individual ACEs and access lists, can't remove or change access group commands, must ensure that the finished working lab adheres to the original lab specifications, and no changes to IPv4 routing are allowed on any device. So, speaking of routing, let's see if this guy has a route to that destination. oh, I didn't mean to do ping. Show IP route 3311. Network not in table. Let's look at his IP routing table. Okay, so all he has are connected routes, and then he has one static route. And that static route is a default route, so that should be good enough for him to at least forward the packets on. And if you're looking at the topology diagram, dot 42 belongs to switch 3. So his next hop is switch 3. So right now he's got a default route saying send everything over here to dot 42 as a next hop. Okay, so let's check switch 3 and see what his routing table looks like. Show IP route 3311. Now he does have a route. And he can even ping there. He can even ping the destination. So, what is the situation? Now notice in this particular case, we are getting some interesting syslog messages which might lead us down the troubleshooting path where we need to go. It says, CDP has detected a native VLAN mismatch on fast Ethernet 0, kind of cut off there, but 015, 2, and 1. So apparently there's some kind of native VLAN mismatch on 015, and it looks like 014 as well. So if we look at our topology diagram, the physical layer topology diagram right here, that native VLAN mismatch is on these links between switch 3 and switch 1. All right, let's go ahead and fix that, whatever that is, and see if that resolves our problem. So, show run interface fast Ethernet 0/14. So this says switch port trunk native VLAN 2, and if you remember from the LAN switching portion of this lab, that 14 and 15 were put into an ether channel, and we see that right here. Show ether channel summary, and we see the ether channel is up and functional. So this side of the ether channel believes that the native VLAN should be 2. Show interface trunk. Yep, port channel 1. It's up, it's functional, trunking with native VLAN 2. What does switch 2 believe? Show ether channel summary. Okay, well here we have a problem because he's not even in an ether channel. So ether channel is not functional on his side, and we know it's supposed to be. Show run, begin. Let's just do show run. Because when you use begin and include, you always have to get everything case sensitive. So 14 and 15, here we go. Ah, well, that's a problem. 14 and 15 are shut down. Okay. Well, according to this, we are not allowed to make any changes to the physical layer. All right, so that means that these links might as well not even be here because these ports are shut down. We're not allowed to bring them up. So that being the case then, the only way that this is going to work is if R2 can send his packets to switch 1 and then they can be bridged in this direction. Clearly that's not happening because the ping is not working. So something is wrong with this connection. This path is not functional. If it was, then R2 static route would reach switch 3 and switch 3's OSPF route would get those pings where they need to go. And it's not working. So we can't change this interface right here that's down. Let's see what's going on with this path and why that path is not open to us. So the first thing I'm going to check is while I'm in switch 1, because that's where I am right now, I'm going to check the status of interfaces 10 and 11. Check to see that they're physically up and functional, and make sure that they're both VLAN trunks, because according to our previous lab where we built all this, both those ports should be in VLAN trunking mode. So let's start with that, 10 and 11 on switch 1. Show interface trunk. Okay. So 10 and 11 on, oh wait, we're not on switch 1, we're on switch 2 right now. Okay, that may have been my mistake. I was thinking we were on switch 1. Let's just check the port channel again. Show ether channel summary. Okay, this looks better. So the ether channel actually is functional. Common mistake when you're dealing with terminal servers, going to the wrong device. Okay, so on switch number 1, show ether channel summary, we see that the ether channel is functional. Okay. Show interface trunk. Shows us that 14 and 15 are trunking. But yeah, we definitely have a native VLAN mismatch where it's 1 on one side and 2 on the other. So let's think about this for a moment before I change anything. Why would this cause our problem? Well, if you remember from when we built this in the first place, this port right here on switch 1 is part of VLAN 2 and VLAN 3. It's trunking. And this interface here on router 2 was trunking, broken up into sub-interfaces. Now we just saw that router 2 has a default route going to address .42, which is switch 3. And that is VLAN 2. That is interface VLAN 2 on switch 3, which tells me that when router 2 is sending his traffic to reach his destination, he's going to send it up this way on VLAN 2. And then when it goes out switch 1, remember we have an ether channel right here. Well, here's our question. Which direction is it going to take? We can't just assume it's going to take the ether channel. We have to look at the spanning tree topology and figure out, as far as VLAN 2 is concerned, how does switch 1 get to switch 3 on VLAN 2? When switch 1 gets a VLAN 2 frame that needs to eventually get up here, which path does he take? Does he go out the port channel? Or does he go down one of these links here? Because maybe we don't even have to troubleshoot the port channel if spanning tree says, oh hey, that's blocked. I don't go that way anyway. So let's see which path is open from a spanning tree perspective on switch 1 for VLAN 2. So I'm going to turn off console logging so we don't get interrupted with this. Okay, show spanning dash tree VLAN 2. All right, so the port channel right now is in blocking state. It says PVID inconsistent. We're getting this message because of that native VLAN mismatch. The native VLAN mismatch is causing this to go into the blocking state. So right now, but we are open on 0/11. 0/11 is an open forwarding path. And we know that if we have a root port on one side, the other side has to be open as a designated port. So at the moment, when router 2 sends his frames up on VLAN 2, they're going across this way, also on VLAN 2. Okay? So then when switch 2 gets them, why doesn't he continue to forward them on VLAN 2 up to switch 3? Let's see. Is switch 2 somehow prevented from doing that? So let's check the spanning tree state on switch 2. Show spanning dash tree VLAN 2. So here's our problem. As far as switch 2 is concerned, his interfaces leading upstream to switch 3 are blocked, also because of a native VLAN mismatch. So to summarize what we found so far, from a VLAN 2 perspective, switch 1 cannot go this way because there's a native VLAN mismatch. So these interfaces are blocked. But he is open this way. Switch 2 cannot forward them this way because these are blocked, because there's a native VLAN mismatch on these interfaces. So that's why there's no way for router 2 to get his packets to switch 3, because he's blocked in all directions. So we have a choice at this point. We got to fix this native VLAN mismatch problem. Ideally, we would fix it on all 4 of these links. These links right here, we need to fix it, and these links right here. Technically speaking, if we want to fix our problem of allowing router 2 to get his frames to switch 3, we can choose. As long as we fix one of these links and get the native VLAN matched on both sides, router 2 will have a forwarding path to get to switch 3. So let's fix the port channel. Let's fix it right here. Let's fix the native VLAN and get it working there. So at least router 2 has a forwarding path to get to where he needs to go. Now, when we did the original lab, when we built this, there was nothing in the original lab that said anything about the native VLAN on this port channel. The only time the native VLAN was ever told to be changed was right here on this trunk. So originally the native VLAN was 1 on that port channel. So let's set it back to 1. Whichever side is not 1, that's the side we need to fix. Okay, so let's go back to switch number 1. Show interface, show run, interface fast Ethernet 0/14. Okay, no mention of native VLAN there. No mention of native VLAN there. Show run interface port channel 1. Let's check out the port channel. No mention of native VLAN there. So the native VLAN, it must be wrong on switch 3. Show run interface fast Ethernet 0/14. Yeah, so this is incorrect. Okay, now when interfaces are bundled into a port channel, you really should not be making changes to the physical interface when you need to make configuration changes. You should be going to the port channel interface and making your changes there. So that's what I'm going to do. I'm going to go to interface port-channel 1 because these guys are in channel group 1. I'm going to shut it down, which would also shut down the physical links because they're bound to it. And then from here, I'm going to say switch port trunk native VLAN 1. And now let's bring it back up. And the physical links should inherit that configuration change. Let's see if they did. Yes, they did. Okay, line protocol is up, port channel state changed to up. All right, let's go back on switch 1 and see if he's still blocking on that side of the port channel for VLAN 2. Nope, now the port channel is in the learning state. It's soon going to be forwarding. As soon as it's forwarding, we should have an open path all the way from router 2 up to switch 3. And that should solve our ping problem. Okay, it's forwarding now. So at this point, when we initiate our ping from router 2 to the loopback of R1, it should go up this way on VLAN 2. It should go across the Ether channel, and then switch 3 already has an OSPF route. So switch 3 will then route it, and it should go down. Let's verify that. And now our ping is successful. Now, we could leave at this point. At this point, we fixed our problem. If this was a real production network, though, remember, we also saw that there was also a native VLAN mismatch on these links right here between switch 2 and switch 3. I'm not going to fix that, but in reality, if this is a real network, we probably should. We should fix that native VLAN mismatch as well. But we have technically fixed the problem, which was a native VLAN mismatch.